Welcome back. I guess it's time to start. Just starting where we left off. Basically having 5 more talks before we go for brainstorming. I will start and I will talk about antibody glycosylation. So I'm going to keep it simple. I'm not going to talk about a lot of glycomics, but only one side on the FC portion of the IgG, and talk more about the function and what we have learned in the last, well, a decade and a half, I think, together with Manfred mostly, in deciphering what's going on, basically. So what I'm going to talk about is IgG responses, which you know are occurring in different subclasses. Really important for the effector functions of these antibodies, and of course, depending on the subclass, they interact differently with the Fc gamma receptors of myeloid cells and NK cells, but also differently with complement. We all know that this is really important for their effector functions. But what I'm going to talk about is how glycan switches actually create this alternative universe, what I call it, of these subclasses, and basically change the effector landscape of these antibodies, both from the perspective of Fc receptors and complement. And I'm going to talk about what these switches and modulators are, and you probably all know them. You also know these structures, so I can basically speed run through the first part, which is I talked about a lot before, which is the afucosylation of these antibodies. So basically, you know the antibodies, they have these recognition arms, the FAP arms on the top, encoded both by the heavy and light chains, but the business arm of the antibodies, the effector arm, the constant region, which is not really that constant because of the glycans, which are in the FC region, is actually very variable, and you all know that. I don't have to go through this, so I can use the speed run feature of, because you're all experts. But what I'm going to really focus on in the first part, really quickly, is this difference is between the IgG glycosylation, although being really variable. Most of the antibodies are fucosylated, and only this minor fraction is afucosylated. But I'm really going to stress that although this is the case, and you would think, well, this is not really important in human biology, is that when you zoom into really specific immune responses, that most indeed antibody responses there, so different boats here are different immune responses, specific responses, are all fucosylated, indicated by the black boats. Some are really different, and some are really with a majority of the antibodies being afucosylated, and this is really important. So when you look at glycosylation of antibodies, you should, of course, it's important to sometimes to look at the total glycosylation, but specificity is sometimes key. So what we did, started I think almost 15 years ago, probably longer, it was to look at in these diseases, in alloimmune responses in pregnancy, where mothers make antibody responses to paternal antigens on cells of the fetus, which are paternal antigens. And very often when these are targeting red cells and platelets, these can really result in really serious life-threatening diseases of the fetus and the newborn, is that the antibody levels, so indicated here basically on the x-axis, is not indicative of severity. And this is basically severity as here being number of platelets found in the fetus. So you have this really dangerous thrombocytopenic under 100 or under 100 or 50 or so, is that you have really increased severity of bleeding. But almost everybody has high level of these antibodies, are in danger of this having very low number of platelets, but also most of the individuals have actually no detectable, almost no detectable antibody levels, but still have very severe disease. So what we started to ask with Manfred was, is there something to the glycans, the most unexplored part of the antibody at the time? And would that suggest something different? And basically, to our big surprise, is that we saw that the specific antibodies, so compared to total antibody glycosylation, so this is fucosylation on the x-axis, total antibodies on the x-axis, and specific antibodies on the y, is that you see, as expected, that the total antibodies are all very highly fucosylated, 94, 95, or something like that on average. But basically, the specific antibodies range from being really highly fucosylated, as you would expect, down to almost nothing. So, and everything in between. So, and to make a very long story short, we saw that these antibody fucosylation features are something that seems to happen early in these immunizations. So, as indicated by the number of pregnancy here on the x-axis, but then turns very stable. And we've seen also an antibody responses without pregnancies or deliberate immunizations in humans, is that once you get this immunization, that can be stable up to more than 10 years, or as far as we have been able to look at. And that these are sort of indicative of serious disease, basically. And the reason is, and I'm again making a very long story short, is that that afucosylation of these antibodies enhances the affinity to certain Fc receptors, or Fc gamma receptor 3, as shown here. So what we did here was to make a panel of antibodies, several panels actually, glycoengineer with either fucose on the left and afucosylate on the right, and then we made them bisected or non-bisected, so in different quadrants here, and then we have them in each quadrant elevated galactosylation, so with almost without galactosylation, and then increased galactosylation, and then the final bar here is always enhanced sialylation. And basically what you see is that with fucose, the affinity is not changing at all, no matter what the other glycans are. If you take off the fucose, then basically you get a bump in affinity up to 20-fold. So this is measured by SPR. And then if you enhance the galactosylation on top of this, it's twofold, or up to 40-fold in total. And if you have some more sialic acid on it, the affinity seems to drop a little bit if the antibodies are bisected, but not really that much. And this is because, so it's only happening for Fc gamma receptor 3, and this is because of this glycan in the Fc receptor 3 family that is sticking into the Fc region. So this is the Fc region here in orange. The Fc gamma receptor is in white, and you have the blue glycan here of the Fc receptor, which is unique for Fc gamma receptor 3 family, sticking into the Fc region. And basically, if the fucose is present in the Fc region, then it's impeded to actually stick in. So if you take off this glycan, basically, of the Fc receptor, the affinity is almost as high as if you take off the fucose in the Fc region. So basically, it's really this fucose is really in the way. So this is resulting in this bump in affinity, basically, here. And this is downstream, if you look at the effector functions, enhancing Fc gamma receptor activities here measured through NK cell-mediated ADCC of red cells. So we made this panel now as anti-D antibody, anti-rhesus antibodies against red cells. And if you have fucosylated antibodies, these antibodies are completely silent. They don't do anything in terms of ADCC. It's only when you take off the fucose, then they start to do something. If you enhance again the level of galactosylation, they become better. And if you enhance the sialylation, it may be slightly decreasing, but not really by that much. It's nothing to call home for, if you would. So basically, to make a long story short indeed, afucosylation is something really unique in alloimmune responses, which we don't understand fully. And it's, you may now also ask yourself if you need to be pregnant to actually make these type of responses. And the answer is really no, because we have also looked at this in men deliberately transfused with rhesus D positive blood in D negative men. They make also antibody responses, which are also very similar in afucosylation as females that are pregnant. Also, this is seen in people, men that are transfused. So you don't need to be pregnant. You can also transfuse red platelets. You make HLA antibodies, which are found on the platelets, HLA molecules. This is also found in kidney transplantation. HLA antibodies in kidney transplantation, as shown by Margie Ackerman together again with Manfred, showed that these HLA antibodies can also be afucosylated. And if you have this afucosylated phenotype, it correlates also with rejection of the kidney. So basically the question is, why are we making these antibodies in pregnancies? Because if there is anything, you should not make dangerous antibodies in pregnancies, because evolutionary, you want to keep that fetus as safe as possible. Because these are so unique responses, I really have to stress this. If you look at total IgG, we all know this, IgG are almost fully fucosylated. If you look at specific responses, so people have done that in a handful of publications, looked at tetanus toxoid, all kinds of immune responses in vaccines, and they're all highly fucosylated, almost 100% fucosylated antibodies. But only these allo antibodies seem to be capable of making afucosylated IgGs. So we thought that perhaps there is something unique with how the B cell is recognizing these antigens, because obviously these are soluble antigens. And these are not. These are on the surface of cells, and they have, of course, all kinds of receptors that have also triggers for cells, like checkpoint inhibitors and all kinds of similar type of receptors, maintaining other responses. So basically, the B cells, through the B cell receptor, recognizes the foreign antigens, but always in the context of cells. So perhaps this is the key, and may explain perhaps why other publications also showing afucosylated antibodies in HIV. So Margie Ackerman again, together with Khalid Alter, showed also at similar time that HIV antibodies also, in HIV you can also make specific antibodies that are afucosylated. And the group of Jeffrey Ravitz also showed that dengue antibody in dengue are also afucosylated, correlating with really enhanced Fc gamma receptor 3 activities. So perhaps this is something, a common feature found in also in enveloped viruses, because that's also a very similar type of response, how the B cell properly recognizes these glycoproteins in the foreign, on the host of other cells in the context of self. And basically, we looked at several enveloped viruses, such as CMV, also HIV again, and we see indeed afucosylated antibodies that is similar to our antibodies against platelets. We also see this for HPV, to a lesser degree, also mumps and measles, but mostly only more stronger if you see this by natural immunization and not by vaccination in terms of HPV, but for mumps and measles, which are actually attenuated viruses, it's very similar to what you see in nature, in natural immune responses. And this is not seen against non-enveloped viruses, which do not have glycoproteins on the host cells. So basically, this seems to be the case, but that you need to have a foreign protein to make afucosylated antibodies. You need to have a foreign protein on the surface of self. And to take this a little bit further, because we thought, well, if this is an evolutionary important trait to make antibodies against enveloped viruses, and this is why we make it also in pregnancy, because the antigen looks similar from the perspective of B cells or something else, that perhaps this is also important in malaria infections, because those are having parasites that are expressed in red blood cells, forming these anchor proteins basically in red cells, really transforming the cells to adhere on endothelial cells so they're not gobbled up in the spleen by macrophages. And basically we looked at immune responses to those proteins, and indeed those proteins and antibody responses to them are extremely afucosylated. Now everybody has afucosylated antibodies and down to almost to the same level as we saw in alloimmune responses, but it's highly variable. So these are antigens we see from birth on in endemic region, and these are antigens found on placenta, because that's a new vascular niche that is also amenable for propagation of malaria pathogens. So when you become pregnant, that is an increased risk for new episodes of malaria. And basically looking at those responses, you see that the number of pregnancies seem to associate with increased level of afucosylation, basically, or decreased fucosylation, if you will, as a sort of a surrogate factor of correlation of the number of malaria infections you have. And also for the antigens you see from birth on, basically the afucosylation level or fucosylation level really drops with age, also a correlate of the number of infections that you see in this region. So basically, it looks like, at least the malaria pathogens, that the more number of infections you go through, the stronger afucosylation response you make. And I really also want to stress is that you, with the same antigen, that now used as a protein conjugate vaccine, does not, absolutely not, make afucosylated responses. As you see here, they are 100% fucosylated. So you really need this infection or probably what we think the cellular sort of expression to get this type of response. And these responses are, of course, also highly, much more effective in terms of NK cell mediated activity through Fc gamma receptor 3. And then we asked the question, so whether or not this is something that is for the vaccines, because the new vaccines in COVID-19 were mRNA vaccines and also adenoviral vaccines, basically transmitting messages to our host cells to produce this protein. Similar type of visibility from B cell perspective as in COVID-19. And as you may know also, in COVID-19 we see that there is a tendency to make afucosylated antibodies in the beginning of the response, so in naive individuals, when they seroconvert, and this is more stronger in people that are really heavily sick. It's much less, or it's less in people that are less sick, and also if you have actually vaccination, it's to a very similar degree. This is completely different from malaria and the alloimmunization that I mentioned, because it's a transient thing. So if you look in a matter of weeks, you actually goes up and becomes almost fully fucosylated. But then if you get an immunization afterwards, you start highly fucosylated because it goes up, and then it goes down again, it seems. What we now ask ourselves, what is happening if we now get new infections? Is this now being accumulated or in time, or is it staying stable? We at the moment, we don't know, but we look forward to look at this in more detail in the future. And now I want to start that I really wanted to talk about, but I wanted to do a speedrun of this, but I didn't. I completely failed about that. So I hope I have some time to talk about this calcisulation effect, which we see is that it's extremely high in all types of immunizations. If you have a mild infection, or if you have really serious disease, you start off with really high level of calculation in specific S antibodies in COVID-19, also in vaccines, immunization. But if you have a really serious disease, or you are hospitalized on ICUs, you see that in a matter of weeks, it actually drops really, really quickly. So the specific antibodies are dropping like this. And actually, you also see this also happening in total IgG glycosylation. Only in the ICU individuals, the calculation is dropping to a similar degree as well as these antibodies. Perhaps not similar degrees, because this is, of course, going from 80 down to 30%. And this is actually mostly older individuals. I can't really see, I think it's from 60, 50 down to 40, 30% in time. But this is absolutely not happening if you have a mild course of disease. So calculation of total IgG is not changed. So the question is, what is happening? Is it perhaps the calculation is sort of a happening following an inflammation? And basically, you all know that calculation is changing in time. A very seminal work from a genus group showing that how this is changing in time. And basically, you as a community also have been working on this. In a lot of autoimmune diseases, you see these acalculation features, which we associate with pro-inflammatory antibodies. And I'm also guilty of this and publishing all that we do that because this is something we all see. And also very seminal publications from 10 years ago or 15, 20 years ago really sort of pushed this field to increase our curiosity about antibody glycosylation, because there was supposedly also a new type of receptors called type 2 receptors that may be associated with this inflammation. And so having sialylated antibodies recognized by these receptors, DC-SINE and CD23, basically, and the question is this really true? So a lot of studies have actually looked at this, and we did this as well, and I never really discussed this, we only published this. So we made antibodies that we glycoengineered only both in the FC and also in the FAP, with either afucosylation or highly calcisylated and sialylated, but also without sialic acid, both in the FC and also in the FAP region, and basically made HEX cells to either express classical FC receptors or CD23 or DC-SINE, and looked for their expression by antibodies, and indeed that they are indeed expressed by receptor antibodies, but you also see that they bind their ligand. Fc gamma receptor 2 binds IgG1, Fc epsilon gamma receptor or CD23 binds IgE as expected, and DC-SINE binds ICAM3, which is a known ligand for DC-SINE. But when we look at binding, this is by flow, by these antibodies, we don't see any traces of binding to DC-SINE or CD23 by either FAP or FC glycosylated antibodies, no matter how you glycoengineer these. Only the Fc gamma receptor 2 is binding to all these antibodies and not discriminating. So the question is, of course, this is by flow. We're looking at monovalent interaction. Perhaps these are low affinity interactions. So what we did this is work by Robin Temming, that we did was to use cellular SPR by looking at avidity interactions. And what we do is that we coat or conjugate our antigen, in this case human serum albumin, conjugated with heptin, TMP, and then we have TMP-related antibodies that we deposit on these chips, and then we flow the cell over it so we can monitor multivalent interaction of those cells. And basically we see that cells expressing Fc gamma receptor 2A, they bind to Fc gamma receptor IgG on those surfaces, and anti-CD23 antibodies are recognizing the CD23 transfected cells, and anti-DC sign are recognizing DC sign. So you see under these flow conditions. But if you look at the binding of these of just the antibodies glycoengineered either with FC or FAP glycosylated antibodies, either silated or not, we only see binding of the Fc gamma receptor 2 expressing cells, and CD23 or DC9 do not recognize antibodies at all, no matter how they're glycosylated. So basically, we think that we should be really careful, at least in humans, because this is a fully human system, that these type 2 type of receptors are real, that these antibodies actually, having highly calculated antibodies actually, instead of being anti-inflammatory or pro-inflammatory, that they are actually really, so the other way around, having calculated antibodies are pro-inflammatory. And I'm going to really do this in a speed, basically go to the summary, is that what we have seen by glycoengineering, but also protein engineering, is that if you enhance calculation, is that these antibodies, that the calculation is enhancing hexamerization of these antibodies on the surface of cells, enhancing C1q binding and activating complement downstream, basically. And we've seen this with all kinds of antibodies, by the heptin antibodies, also HLA antibodies, and you're seeing this here, basically, C1q binding and C3 binding. So these are non-engineered antibodies. If you enhance calculation, cellulation on top, you see that enhanced calculated antibodies are really enhancing C1q binding and also downstream C3 activity. And cellulation on top of this doesn't do anything, basically. And this is the same cases with anti-HBV1A antibodies. And also in vivo, in humans, people receiving platelet transfusion, what we see is that the level of antibodies against HLA, so people with HLA antibodies, are not associated with the clearance of these platelets. So this is platelet clearance on the y-axis, and the amount of antibodies is not really correlated with that, or the polyclonality of that response. But galactosylation is. So the higher the galactosylation, the faster the platelets are seen to be cleared from this, from these patients. And we think that this is complement mediated. So basically summarizing, we think that there are two types of glycans that are really controlling antibody effector functions. And that is, first of all, the fucose. That is a natural thing that we are making in terms of envelope viral infected cells, something that we also make really strongly in malaria type of infections to infected red cells. We also make this in pregnancies to alloimmunization, and we think that may be a sort of a evolutionary choice or something that we have to accept in evolutionary terms, because these types of immune responses are not that common. But of course, in endemic region, enveloped viruses and of course malaria are important pathogens to clear off. But it can also turn against us, because as we've seen in dengue, or Jeffrey Ravitz and have shown that in dengue, if you have afucosylated responses that are associated with pathogenicity, in early COVID-19, it also seemed to do that, although it may also, in longer terms, associated with positive protective traits. And calculation, completely different from what we, I guess, in some early days thought, is that calculation is controlling this hexamerization of antibodies binding to C1q and enhancing complement activity. And it's basically a protective trait, but can also be in autoimmunity a pro-inflammatory thing. But it's much more malleable and is changing with inflammation. And as we age, we acquire these antibodies and perhaps also inflammatory type of antibodies. And with that, I think I would just like to end, and thank you very much for your attention, and thank all the PhD students and technicians and postdocs that helped us with this, and also collaborators throughout the years, and also, of course, mostly the lab of Manfred Wöhr and Manfred himself that we have collaborated with for a very long time on this. Thank you very much. I think perhaps to set a very good example, I will just ask you to refrain from questions and come to me in the coffee break or during drinks, dinner, or whatever, if you have any questions. And welcome the next speaker, Anand Mehta from Medical University of South Carolina, who is going to talk about single-cell glycan analysis. I'm not a Mac person, so can you perhaps try that?
I am a Mac person. It's frozen, I think. There it goes.